We will now do a very important theorem. This shows where we are going to imitate many things, many properties of finite dimensional operators. So this is called the Riesz-Fredholm theory. So, definition: V Banach space, an operator in LV is said to be a compact perturbation of identity if it is of the form I minus t, where t in LV is compact. Such operators are very important because they help us to study the spectrum of compact operators on one hand, and secondly they imitate a lot of the properties of finite dimensional operators. So we have this important theorem which we will prove slowly. So theorem. So this is called sometimes the Fredholm alternative. I have already used this terminology earlier and we will comment on it at the end of the proof of this theorem. So let V be a Banach space and let T in LV be compact. Let T star be its adjoint. Then A null space of I minus t is finite dimensional. B range of I minus t is closed and range of I minus t is null space of I minus t star. The second part we know already. We have already said if it's closed, then you can give it in terms of this. Then C, null space of I minus t is 0 if and only if range of I minus t equals V. So null space of I minus t is 0 means it's an injective map or 1 1, and this range of I minus t equals V means it's surjective. So this is exactly like in finite dimensions. Range of I minus t is 1 1. I mean I minus t is 1 1 if and only if it is onto. Okay. Then D, dimension of null space of I minus t equals dimension of the null space of I minus t star. Now in finite dimensions we have also this. If you took the rank nullity theorem into account, then it will be range of I minus t equals range of I minus t star, which is the famous statement that the row rank of a matrix is the column rank. Okay, so this is just the corresponding version, infinite dimensional analog of it for operators which are compact perturbations of identity. So let us prove this theorem So proof A. So let B1 be the closed unit ball in n of I minus t. N of I minus t is closed, so it's a Banach space in its own right, and B1 is the closed unit ball. So if x belongs to B1, then what do we have? X equals Tx. So B1 is contained in TB, because where B is the closed unit ball in V. After all, n of I minus t is a subspace of V, so B1 itself is a part of is a subset of B, and if you took x, then x is equal to t of x, so it is t of something. So again, so B1 can be thought of as the same, but TB closure is compact, and B1 is a closed subspace of a compact set, and therefore implies B1 is compact. And if you have that the closed unit ball is compact, the space must be finite dimensional, so is finite dimensional. Okay, now let's prove B. So we have to show the range of I minus t is closed, and of course the second part of it is easy, because we have already seen if you have a closed range, then it is equal to the annihilator of the null space of the adjoint. So that part is well known. Okay, so let Fn belong to range of I minus t. Let Fn converge to F in B. So to show F belongs to range of I minus t. Okay. So Fn is in the range, so this will be un minus tun, un in B. Now n of I minus t is finite dimensional, so this implies that there exists a Vn in n of I minus t such that norm of un minus Vn is in fact the distance of un from n of I minus t. Why is this so? Okay. Now what is distance of un from n of I minus t? It is nothing but the infimum of norm of un minus V for all V in n of I minus t. So you take a sequence, say Vm, which converges to un minus Vm converges to the distance, but then you are in finite dimensional space, therefore a bounded sequence has a convergent subsequence, and therefore the limit of that convergent subsequence will be in fact the point. So always the minimizer is realized, and therefore if you have a finite dimensional space, you can always find a Vn such that un minus Vn is this. So I have orally mentioned this solution, so please write down the arguments so that you will be clear about it. So you take a minimizing sequence and it will have a convergent subsequence, and that limit should be precisely the element which you are looking for. Okay, so you can have this, and therefore we can write Fn as un minus Vn minus t of un minus Vn, because un minus tvn is 0, so I am just adding 0 to this, so there is nothing more. So now we are going to make a claim. Un minus Vn is bounded in B, so it's a bounded sequence. Okay, so if not, there exists a subsequence norm such that norm unk minus vnk tends to plus infinity. Okay, so now you define W and K equal to U and K minus V and K by norm U and K minus V and K. So norm W and K equal to 1. And what is W and K minus T of W and K? Well, that's U and K minus V and K by something. So you just get F and K by norm of U and K minus V and K. And this denominator goes to infinity. Numerator is Fn goes to F, so it's a convergent sequence, so it's bounded. So bounded divided by something going to infinity. So this goes to 0 as K tends to. So W and K minus T of W and K goes to 0. Now W and K is bounded because it's of norm 1. So there exists a further subsequence such that T of W and K L is convergent. So let T of W and K L go to Z, but then W and K and T W and K have the same limit, so this implies that W and K L also goes to Z. Then T of W and KL should go to TZ, and therefore this implies that Z equals TZ, or Z belongs to N of I minus T. Okay. Now V N K L belongs to N of I minus T, and therefore the distance of W and KL from N of I minus T is nothing but this distance of U and KL from N of I minus T divided by norm of U and KL minus W and KL. But because I am dividing, W and KL is this. Now, distance of U and KL from NIT is precisely what is in the denominator. Sorry, V and KL, not W and KL. Okay, U and KL minus V and KL. Okay. And therefore, this is in fact equal to 1. So, on one hand, d of W and KL from N of I minus T equal to 1 for all L, and W and KL converges to Z on the other hand, which belongs to N of I minus T, and that's a contradiction. That's not possible, and therefore claim is established. That is, Un minus Vn is bounded. So T is compact, implies there exists subsequence such that T of Un k minus Vn k converges to some, say, H, say. Because T is compact, so given a bounded sequence, you have a convergent subsequence. Let's say, okay, let me call it G. Okay. So U of Nk minus Vnk minus T of Unk minus Vnk equal to F. f and k. So this converges to f, this converges to g, so u and k minus v and k should converge to f plus g. So t of u and k minus v and k should go to tf plus tg, and that is equal to, but it also goes to g, so this is equal to g. Let us call this h, so, and that's equal to th. So th is equal to g, so th minus h or h minus th is f plus g minus g, and that is f, and therefore this says that f belongs to range of I minus t. Okay, therefore range of I minus t is closed. And once you have that, that automatically implies that range of I minus t is nothing but the null space of I minus t star. Okay, so next we will take up the other part presently.